What's going on, YouTube? This is Just Cross, and we're back with another reviewing video. You see, the finals is upon us. Finals week begins for me in like a couple of days. So what we're going to do is this proving exam, or I'm going to explain that this proving exam is definitely going to be the hardest one that I have, relatively, I think. And I need a review for it. And there was 3 chapters plus some extra stuff at the end that I don't even know will be on the exam. And the exam that I made a video for, that exam I did the best on, and I can acknowledge that that was also the easiest exam. However, I did the best on it, and I'm a man of superstition, so I'm gonna do it again. I'm gonna review 1 chapter a day. Hopefully, I need to kind of review the 1 chapter a day because my exam is like on Saturday. So we're gonna start from the basics. Proofing, we had 3 main chapters. You saw the 3rd chapter, that was basically all about cardinality. And that used already a lot of the tenets we established in set theory, which is where we will begin our beautiful journey. And by beautiful, absolutely awful journey. And I have my notes right next to me, and I'm going to basically just be writing definitions down. But first I can explain what is a set. What is a set? In an undefined sort of, or like in a primitive sort of way, a set's just a collection of objects, and each object is called an element of said set. We can, with the notation that X is a set, X in X is an element. Element of X. Seem easy enough, relatively. So, we have our first definition already, which is not even like defining one set or another. 2 sets, I'm going to write down the whole thing, 2 sets, A and B, are equal, A equals B, if and only if they have the same elements. A lot of this will be fucking basic. They have the same elements. I'm writing really big, which means I'm going to have to make a lot of new pages. That kind of seems self-explanatory, and basically it says, in our example, we have for X in A, that implies that X is in B if A equals B. That, is a sign we'll be using a lot, or this is equivalent, and then this is implies, implication arrows, the vibes, the vibes. Another remark is that sets are unordered. So like if we have A is equal to 1, 2, 3, we can also say that A is equal to 2, 3, 1, da, da, da. The permutations and combinations of such. But let's move on, because we already need to make a new page, so I'm going to kind of try to write smaller, and I'm going to change the color to blue. So the empty set is a very specific, funky guy. The empty set, denoted by that, is the unique set that has no elements at all. It's its own unique set, and I don't know why. Or like it's important because that is often a specific case in a lot of proofs. It is denoted as that. Those are the set brackets. It is not, because this is the set with 1 element, which is namely the empty set. And that's where you can kind of get weird. It's like a nesting doll of like empty sets if you start making sets that have the only element being an empty set kind of way. Okay, so I don't know. We also then went over some set builder notation, which is basically like we basically said we have x and then p of x, which basically says that object x has property p. And I can try to think of an example off the top of my head. So like, I don't know, like, fuck. All right. I'm not gonna. Huh. Um. So example is let p be the property being a natural number between 1 and 3. So the set of that, the set with x with that property would be equal to just 1, 2, 3. Or you can write it in the set builder notation as x is an element of the natural numbers with the property that x is between 1 and 3. That that's kind of that was kind of a gimme. Anyway, I also could have made it like a division class, like x fucking whatever, don't care. Brain is too fried to think about it. I need to study anyway. Coming up with my own examples will not help me study. We can say Russell's paradox real quick. That's a quick. Russell's paradox is basically there is no set of all sets. Basically, you can say that, oh, there are sets with everything. So there's like n, which is set of natural numbers. I forgot the n. Natural numbers, etc. I spelled numbers wrong too. You have z, which is your integers. You have q, which is fractions and stuff. And you have r, which is your reals. You have I think, or something along that lines, which is like irrationals and stuff like that. And you have like c, which is complex. And you have sets that are everything. It's like n is the set of all natural numbers, but there cannot be a set containing every set because it violates the axiom of separation. But riveting. That I don't think is really important. And then we went over two real quick quantifiers, which is basically math language, math and logic language. Basically, there are two things that we have to say often when we're proofing, and it's much easier just to make a symbol for it. There are two. This is there exists. This is very helpful for naming an element, basically. So, and then this is for all. Like, so you can say, like, for all x in n, there exists a y. I don't know, in n such that x plus y is an element of n. That could be true. I don't know. That seems trivial. And in this case, actually, you could replace the such that, I believe, with just that you're such that, which could be your property, x plus y is an element of n as well. But that is simple, and there's also a kind of, I guess, a third. This is a modifier to your quantifier, which is basically an exclamation point, which is there exists a unique. And you can use that, and it's specifically used when defining a bijection, because with the surjection, you need to show that. Okay, let me think. Because this I actually should know, like, actively, so let me think. We can show, like, the uniqueness, like if to have, this is a sidetrack. Injectivity is chapter 2. Injective, it is for all A1, A2 in A, f of A1 equals f of A2 implies that A1 is equal to A2. And then surjective is basically saying everything in the codomain is mapped to. I don't completely remember how to write that out like that, but basically that can show down to bijectivity, which is saying that for yeah, okay, so surjectivity is basically here I can do like surjective. It's I think it's for all A in A, there exists a B in B such that f of A is equal to B. That can, I don't know, I can go over your head if you want. But that basically, you can combine it with the unique symbol to make bijective, or make the definition for bijective, which is for all A in A, there exists a unique B in B such that f of A is equal to B. And the unique part is the injective part. And that is a little sidetrack because I'll have to talk about that like tomorrow. I hope you can't hear that noise every time as well. That is about all I can say there. And then let me take a sip of water before we continue. Let me see how much I have to actually go over. The answer is quite a bit. Okay, so we have A, B are sets. We can say that A is a subset of B if every element in A is also an element of B. I just had to do a shortcut. So basically, if you can, or you can also define A that's not in B if there exists an A in A that, or an X in A, why not, I guess, just to make it easy. Exists an X in A, that X is not in B. And so like if A is equal to 1, 2, and then B is equal to 1, 2, 3, 4, dot, 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 you can say that A is a subset of B. And we can also show the subsets by using, like, by that kind of way. I used dot, 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 which was not a great idea. So we have that the natural numbers are a subset of the integers, which is a subset of the decimals, which is a subset of the real numbers, which is a subset of the complex numbers. Because natural numbers is 1, 2, dot, dot. We can say integers is negative, or dot, 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 negative 1, 0, n, and then so on and so forth with Q and R and complex, which, you know, those complex and R are a little bit harder to actually define or write down. And some easy fact real quick, A is a subset of itself because, I don't know, don't question it, it's kind of obvious. Like, that's actually a pretty good proof, and it's actually our next definition, is that if you have two sets, A and B, two statements are equivalent. These are equivalent, and it's that A is equal to B, and that A is a subset of B, and B is a subset of A. And this will come back. This kind of like definition for equality actually did already appear in cardinality with the Schroeder-Bernstein, which is if that and that implies that they are equal. Good old SB fucking asshole. Anyway, my bad. So basically, those are that. Those are equivalent statements. Basically, they imply each other. Because this is saying that every element in A is an element of B, and this is saying that every element of A is contained within an element, or within B, and then every element in B is contained within every element of A, which also would mean that the cardinality of A is equal to the cardinality of B. But, again, getting ahead of myself. The second implication, basically this one, means that the inclusion, didn't mean that, basically the inclusion part of it, we're about to talk about a subset that's not inclusive, is anti-symmetric. And we're gonna, I spelled it wrong. And we're gonna, I butchered that. There's a second M in there somewhere. And we're gonna talk about it more. Anti-symmetric is important later. However, I'm going to discuss actual subset, or the proper subset next. A proper subset, if we still have two sets, a proper subset, defined like that, is if every element in, here I'll write it, every element in A is in B, but there exists an X in B such that, X is not in A. Basically, B is guaranteed to have more elements. So, at least for the finite case, you can say that cardinality of A is, or B is greater than the cardinality of A due to this fact. So, excuse me, like A is 1, 2, B is 1, 2, 3. A is a proper subset because while every element is contained within B, there exists an element, namely 3, which is not an element of A. That's pretty simple. Again, you can kind of gauge that. You can kind of sense it. It's kind of intuitive to an extent, at least. Excuse me, I'm getting more water. But now we're actually getting some real stuff. So we have A, B sets. We can define the difference between the sets, which is to be the set of X, which is in A, X, which is not in B. Basically, every element in B has been removed from the set of A. So again, I can use a quick finite example. 1, 2, 3 minus 1 is equal to the set 2, 3. That's pretty simple. And then we can also say that A minus B is equal to A prime, which is the complement of A. Or the complement, oops, that's a big mess up actually. The complement of B in A. And then the complement is an actual, you can define a complement in a broader sense if you assume there exists a universal set, namely U. That's going to get confusing. U, to where a complement is U minus A. Basically, a complement is everything not A. And that's, I don't know, complements are actually important in linear. Taking the complement of matrices. I don't know why it took me so long to think about that. My brain is fried and we're already 20 minutes into this video and we still got a lot left, folks. So now we're actually getting into important stuff, and it's union and intersection. And basically their union is defined like that, intersection is defined like that. And the way you can think about it is the words and or. So basically, this is a set of X where X is in A or X is in B. And this is a set of X where X is in A and X is in B. And now how do I define that with the picture? If we take our Venn diagrams, the union is everything. It can be in A, an X can be in A, it can be in B, or it can be in both of them. And then for this one specifically, the intersection is just the middle. It has to be both A and B. And so we can define that A is a subset of A union B. A is a subset of A intersect B. Or, whoops, no. That is the A intersect B is a subset of A. And the same can be said for B. Sorry, I need to like take a breath every once in a while. And there's implications for the elements as well. So basically, if we have an A in A, or not A, let X be an element in A union B, we can say that X is an element of A or X is an element of B, and then the same kind of principle applies to the intersection, where we can say X is an element of A and X is an element of B. It's funky. It's a little funky. And then we can talk about associative laws with the intersections and intersections and unions. So say we have three sets this time. Three sets, A, B, C. So we have A union to B intersect C. Or no. I'm getting ahead of myself. That's foreshadowing. And then we have B intersect C, and we can just say that that is A union B unioned with A union C. Or no, we can't. Oh, I'm again getting ahead of myself. That's literally the exact same. Okay, whatever. You can move the parentheses. That is all I needed to say. You can move the parentheses. Riveting. That's all you need, is that you can move you can move it. And then we can show that with three sets, if we have that A is a subset of C and B is a subset of C, then A union B is also a subset of C. That's an interesting implication, but it's kind of obvious. And then if C is a subset of A, C is a subset of B, then C is a subset of their intersection. Oh, I just dropped a pen. All right, let's take I need to take a breath. I have been speaking a lot. I've been speaking quickly, relatively. We're gonna stop doing that. Jeez. Okay, De Morgan's laws. We've gotten to important things now. De Morgan's laws can be applied to many things. They can be applied to, they are applied later and later again, just basically with different newfangled methods. But basically it has two actual definitions real quick. It has that assuming that there is a universal set, that is an incredible assumption we need to make. You can say that this is the complement. Oh, whoops, no. You know what? Maybe I should stop trying to fucking free solo this. But these make sense. These intuitively make sense because this is a complement. So basically, it's saying that you're taking the complement. If this is your universal set, if the box is your set U, and then this is A and this is B, then this is your union. So this is your, let me change color. This is your A union B. Then you can see that this is your complement of A union B right here. All of this. How do you define that? A complement intersected with B complement. Basically, A complement intersected with B complement, you can say is that U minus A intersected with U minus B. So it is U without all elements, without all X in A, X in B. And that's just an intersection. That's just as simple. And we can say the exact same thing. Let me delete these diagrams. You can say the exact same thing for this one. A intersect B prime complement. We have our universal set. We have our Venn diagram, but this A prime or B prime doesn't even matter. A prime. This is our U. And we can say that the box, including our circles, is that is A intersect B prime, or A prime once again unioned with B prime. So all of U minus A unioned with U minus B. It's nice. It's kind of nice because you can see that we still have, by doing this, we keep elements of B, and then in this we keep elements of A. It's a nice, it makes a lot of sense when you just draw it out, draw it as a picture, basically. And now we have distributive laws, and it was what I was getting at earlier. So if we have two types of distributive, or two cases of a distributive law. A intersect B union C, and then A union B intersect C. And we get A intersect B union to A intersect C, and A union B intersected with A union C. And now, why? 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 We have proofs. I actually do have a proof here. So I'm going to put it into red for proving. So we know that A union or A intersect B is a subset of A, and we know that A intersect B is a subset of B unioned to C, because every element in B is also in B or union to C. So both of those send us with an implication that A intersect B is a subset of A intersected with B union C. And then we can also say that A intersected with C is a subset of A, because it is, and we can say that A intersected with C is also a subset of B union to C. And that implication gives us that A intersected with C is a subset of A intersected with B union C. And we can see that they are both subsets. Those both imply that, whatever, we're just gonna, we're gonna adjust, or is a subset of A intersect B union C. And we can show it in the other direction as well. We can show that the other direction, we basically show that A union B intersect with A union C is equal to A union with B intersect C, by declaring an element, basically. We can use an elemental case, as I have so lovingly deemed it. So we want to show that if X is an element in A intersected with B union C, that implies that X is an element of A intersected with B union with A intersector with C. And then, so if X is an element of here, it's an intersection. So that means that both X is an element of A and that X is an element of B union with C. So it's X is an element of A and, and X is an element of B, or X is an element of C. And so the and implies an intersection, but the or implies a union. So basically what you can say is that X is an element of A intersected with B, or, and the or is your union, A intersected with C. That's pretty simple, kind of. And so your proof is done. And we can do it in the other direction as well. The second one, I believe I didn't even write it down, or I kind of wrote it down. A union with B intersected with C is equal to A union B intersected with A union C. That one can be proved kind of the same way. I don't have the proof right in front of me, so I'm not going to. I'm not going to proof off the dome because I don't want to. Excuse me. Now, let's do some, to another definition. Two sets are called disjoint. Basically, we got two sets. A, B are disjoint if A intersecting B is equal to the empty set. If they have no elements in common, and we can basically rewrite this as, or we can rewrite it, they have another sign, that is the disjoint union of A and B. And so that's helpful in general later. That's an important definition, is that there's some that require that. There are some definitions that require, and some formulas that require the disjoint sets, such as the sum of cardinalities, I believe. But I'll think about that later. Now, next we have to talk about symmetric difference. Symmetric difference, we have two sets, and it's written like this. And that is equal to A union B minus A intersect B. So it's basically, in the Venn diagram, it is all of that. You basically do not, you leave out the middle. Okay, that's pretty simple. Oh, whoops. No. I wrote down the wrong thing. What did I even write down? I don't know, but the picture's right. That I switched up the signs. That one's, well, wait, hold on. That I feel can still be right, but I'm not gonna test it. I'm gonna just write down the real definition and explain it in that way. A minus B unioned with B minus A. Or it's basically also the disjoint union of A and B. So we have a concrete example, 1, 2, 3, 4. Symmetric difference with 3, 4, 5, and you get the set 1, 2, 5. Because it's just what elements are in this set that's not in this set, and what elements are in this set that's not in that set. Kind of a type of way. Oh, no, literally, oh my god, I literally had it right. I just read the wrong definition. Okay. Or I read later down onto the page that, you know what? There's properties. I was reading the properties. Properties of your symmetric difference. Of symmetric difference. We have that asymmetric difference with B is equal to A union B minus A intersect B. And that is, again, I just clacked my teeth. That is, again, intuitive. Symmetric difference of a set and itself is the empty set. Symmetric difference of the set and the empty set is itself. And you can, this is true. Let me, I guess, just write it out so I can say that I went over it. This is also true. That proof was was brutal. That proof was absolutely painstaking. And now we get to something a little bit more weird. And we also get to fucking near the end of the chapter, I hope. God damn. Yeah, roughly. Okay. So we have indexed family of sets. We can say that an indexed family of sets is defined by AI with an I in I. Yeah, follow me. Where your I, cap I, is your index. And your I is a set, so like you can also define it as AI, I, and I. Where I is a set that is usually defined. It's called the index set, the index. And each AI is a set for every I and I. And we always assume that I is not, cap I is not the empty set. That's a weird way to explain it. So we can, here we have an example where we have our I. We can define an I by saying that we have a P in N, where P, with the property P is prime. And so we can say that P Z is equal to PZ, where with the property Z in Z to AP. So the family AP, P and I is equal to the set PZ, P and I. Do you get it? It's kind of weird to think about. There's also another example about like circles, but like I didn't understand that example when it was explained in class. But this generally isn't really important until later, and it gets re-explained better, in my opinion, later, or reintroduced later. So we're just gonna move on to. We have to use it as a definition basically if AI, I and I is an index family of sets. We can define the union, the big boy union, I and I of AI to equal the set of X with X in the set AI for at least one I and I. Basically, this is the set of X with the property there exists an X in AI such that X, or there exists, oh fuck, I got ahead of myself. There exists an I in I such that X is in AI. basically, and you can assume that the other boy, the intersection is coming. Or you can say the opposite, basically. X is in AI for all I in I. And I already kind of wrote it in quantifier form. However, I will do it again. X, there exists that for all X in AI, or no, fuck, for all I, I'm going to erase it, for all I in I, X is in AI. That's fine and dandy. I can give you some examples real quick to make it even easier to even think about. We have, one sec. So we have an index set. The set is 1, 2. So that's not even an I. That looks awful. So we can say that AI with I and I is equal to A1, A2. Fair enough. So we have that the union from an I and I of AIs, basically that is again X, where X is an element of at least one AI. We can say that we have X, where X is an element of AI, or A1 union to A2. Or, well, yeah, basically that. So that's kind of simple, and we can say that the intersection, or which is just equal to A1 union A2. And then we can also say the intersection I and I is equal to, basically, or of AI is A1 intersect A2 for the exact same reason, is that X has to be in A1 and X has to be in A2, which leads to your intersection there. Excuse me for getting ahead of myself and scatterbrained. This next thing, the generalized distributive law for sets, it is a bitch. It is a lot. The proofs are a lot. We have two. We have A intersected with the union of B, I, and that is equal to the union of the intersection and vice versa. Because the shit is kinda the same. These kind of rules are kind of the same after a while. Basically, you flip the sign and you include things. So basically, that's cool and all. That's really cool. The proofs are very difficult, or not even very difficult. There's a lot of double inclusion. So I guess I will show the proof of this one, is that the A intersected with the union is the is the intersection of the union. There's the union. The intersection with the union is the union of the intersection. I will show that proof. Or I will prove that right now. The other one will be left as an exercise. So basically, you can show that we have ourselves of X, which is in the union I equals 1, or I in I of A and, or intersected with BI, which that implies, or that is equivalent to saying there exists an I in I such that X is is the element of A intersected with BI, which is by definition of the union. And we can say that that is also equivalent again to saying there exists an I such that X is in A and X is in BI due to the definition of intersections. And then we can say it again. X is in A. We know that for certain. And X, or, whoops, there exists an I and I such that X exists in BI. By logic, because A does not depend on an I. So we can say that again through implication, or through double inclusion, that we have X is an element of A, and we have that X is an element of the union I of BI. That's pretty simple. And you have it there, that proves, effectively, let me just write down what it proves. That proves that, whoops. Nope, no. There you go. That's exactly what it proves. Now we went over a little bit of logic. I'm not going to go over the logic. Logic's lame. My professor specifically ignored the logic. We don't want to know the logic. So we have a set A. Oh my god, okay. It's more of the same. It is more of the same. Ow. I just ripped on my headset. We're at 46 minutes. We gotta kick this into high gear. Good God. But we still got a little bit to go. And by we got this. It'll probably be an hour. So we have another theorem. We have set A. We have an index family. We have that A minus the intersection of BI is equal, or the union is equal to, I spoiled it, the intersection of A minus BI, which in particular is the complement would be equal to BI complement if A is equal to U, the universal set. So basically saying A minus the union of an indexed family of sets is equal to the intersection of A minus the index family. The intersection of, and then that's also just saying that the complement of the union of the internext family of sets is the intersection of the actual indexed family. Complemented. If A is considered the universal set at this point. And then we have the other direction, which I think we should be used to at this point. BI is equal to the union and then the exact same thing is the intersection. BI complemented is equal to the union of the actual complement if A is equal to U, the set. And we can prove this real quick by double inclusion. And by that, we're going to be proving it by a set of equivalences. Proof of A, at least. We have X, which is an element of A minus the union of index family of sets, which is equivalent to saying X is in A and X is not in the indexed family of the union of the indexed family. So we can define it again by using logical. You can say that's not X is an element of union. So then we can continue by saying you're just going to ditto marks and then saying that it's not an element in I that X is an element of BI, and you can distribute the not. And when you distribute a not or negation, you switch your qualifiers. So instead of there exists an I such that X exists in B, you negate everything. So for all I in I, X is not an element of BI. It's actually important. I forgot about that, honestly. Which you can and then do your equivalencies and say for all I in I, we know that X is in A, X is not in BI. So that we know for all I in I, we have X is an element of A minus BI, by definition of minus. So we have that X is an element of the intersection of A minus BI. End of proof. By the definition of the intersection. So, riveting. It is really, set theory is just so interesting. I was gonna say it gets better. It does not get better. It doesn't get better. Set theory is so boring. So if we have an index family, basically, if we have AI with I and I, we can say that it's disjoint if the union, if the intersection is equal to the empty set. And it's pairwise. This is actually important too, actually. I just said actually like 4 times. Is pairwise disjoint if AI intersected with AJ is equal to empty set for all IJ in Z with I not equal to J. So, and then if the index has at least 2 elements, then this implies that if cardinality of I is greater than or equal to 2. I'm already using the words for cardinality and stuff just in case, or just because I have already technically made a video about it and I know the concepts myself. I'm not reviewing it from the site or from the thoughts of a child who did not know it. So we're gonna get into a new page. So the union, the union AI is called disjoint also written as that, which, that's a symbol we've seen before, or the dot. I didn't cover that. It's also, there's a dot above the U. If is pairwise disjoint. I'm not going to write it because I don't have space. Okay, so partitions are kind of important. Partitions of a non-empty set is a family of subsets. Let me write some of it at least. A partition of a non-empty set. A is a family AI with an index I and I of subsets of A. basically that can be just written really quickly as AI and I for all I and I, such that we have A is equal to the pairwise disjoints of AI. A are basically saying A is the disjoint union of the AIs. The disjoint union of the AIs are I and I. And so basically we can have an example. I'm not going to write it. I'm just going to basically say it. So if A is all integers, Z, then we can say index is 1, 2, the set 1, 2. So A1 is equal to 2Z, which is equal to 2Z, which is Z and Z. And then A2, those are even integers. And then A2 can be the odd integers, which is 2Z minus 1. Then A is equal to the pairwise union, or the disjoint union of A1 and A2. So A1, A2 is a partition of Z, so forth. That, that's pretty simple. Now we kind of get to important things a little bit. Just kidding, but still. So power sets. If we have A as a set, where are we on right now? A set. We can define a power set P of A with the basically saying X, where X is a subset of A. Or basically, and then we can also say that is just equal to 2 to the A. So let's do an example. It's the power set of the empty set. You can say that's the empty set, which is the set containing the empty set, which is not the empty set. And then general principle is that the empty set is an element of all power sets due to the empty set technically being an element of A, or A, whoops, not an element, a subset of A. So we can say that, here we can do another example, the power set of 1, 2 is equal to, we have 0, the set 1, the set 2, the set 1, 2. And so you'll note, I defined it as 2 to the A, and if we let our A equal 1, 2, you can see that the power set has exactly, this has 2 elements. Cardinality of A is equal to 2. You can see that the power set of A is equal, or has, cardinality of this power set has 4, which is exactly 2 to the 2. Which kind of is our rule of thumb. So basically we can define it further by saying that if the cardinality of A is equal to n, the cardinality of P of the power set is 2 to the n, which is this fact probably like one of the most important from set theory. This is big in cardinality, but we can go on from there. I don't particularly care. And we can say some additional things. We can say that if A is a subset of B, then the power set of A is a subset of the power set of B. We can say that the power set of A, unioned to the power set of B is equal, or, I don't, I'm just going to keep it going, is equivalent, or is, implies that, or is a subset, That is important. Here, let me erase this. This kind of got jumbled up. Is a subset, because it's not accounting for elements repeated in A and B. That is a big thing. And then we have the power set of A intersected with the power set of B is in fact equal to the power set of A intersected with B. But this is your special case, is that for most instances, unless if A is not a disjoint union, then the cardinality will definitely be greater than or no. Well, cardinality of A union with that. Hold on. That we can prove B, and I can show you what I mean in like 2 seconds. By what I mean, what math means. Okay. Well, just kidding. B is an exercise. I don't feel like finding the answer to that. But I think that was our last thing. I think that was our last thing to prove on set theory. So basically, what do we go through on set theory? We can set theory buzzwords. Wow, I spelled words wrong. And that's why I do math. Set theory buzzwords. We have set. We have a subset. We have elements. We have union. Intersections, even. We have indexes. We have families of sets. We have complements, even. We have disjoint. We have pairwise disjoint, which is more stringent. Oh, and speaking of that, proper subset as well. That doesn't come back often. We have power sets, and I think that is basically all of our buzzwords. We have partition as well. Partitions are kind of important. And I believe, honestly, that those are as many buzzwords as you kind of need. You have your distributive laws, pairwise disjoint. We have our big union, small union. Symmetric difference is important. I did forget about that. Well, and then we can also just add these two together, indexed. Family. We have our symmetric difference. De Morgan. And I think that's about it. That's relatively speaking, that is our set theory buzzwords. Those are everything. Those cover and encompass a lot of introductory set theory. We have our sets, we have our subsets, we have the elements within the sets, we have our unions and intersections of sets, we have our indexes that we use for the indexed family of sets, we have complements of our sets. If we have our universal set, we have disjoints and we have pairwise disjoints, and specifically pairwise disjoint union. And we have our power sets. We have partitions made with our indexed family of sets. We have our symmetric differences between sets. And we have beautiful old De Morgan's laws, which I think is just something like, I don't know. I'm not going to try to do it off the top of my head. I should remember it by my exam, though. Thank you so much for watching, or not. I don't particularly care. This is for me. This is my exam. I gotta pass this bad boy. So chapters, we got 1 out of 3 done. I might speed through the cardinality a lot earlier, or a lot faster than I will tomorrow. Tomorrow will be, I think, the longest because that's functions, Cartesian products, stuff like that. Cartesian products, relations, and functions, which took a goddamn long time. And then cardinality I might kind of speed through. So depending, because I already reviewed it and did a video, but I can still do it again. Thank you so much for watching, or not, I don't care. I have to do this to pass my exam. And I will see you hopefully tomorrow, if I can do it tomorrow as well.